Cool. What's an open set? Christian, what's an open set?
Set where a delta ball with any given value of delta greater than 0. So for epsilon greater than 0, there exists a delta ball.
Epsilon ball.
Or epsilon ball.
Yeah.
Yeah. Such that for
Where's it around?
Around x sub naught. Such that for it's not any for
There's something a little off here.
yeah.
Yeah. How do we tweak this? The essential ingredients are almost all here.
Oh, is it there exists an epsilon greater than 0?
Yeah.
Okay.
But what comes first? What do we take first?
All the elements in the set.
Yeah, so first we take a point in the set. So that's where you got hung up because you didn't have a place to put your ball.
Fair enough.
I think so. Open set. For all x inside the set, there exists that epsilon. You were right about that. You knew there was something weird going on there. Such that the epsilon, and it could be a delta or an epsilon, but that that ball is completely contained inside the set. Does that make sense? Everybody we'll have a quiz probably next week with this will be one of the definition words on it. What does it mean to not be open? So what's the negation? What is a not open set? Like to practice these logic stuffs. How do we start negating things? Camille, I know you've done this with me before. How do we start negating this stuff? Because I remember you doing it quite well.
You switch the quantifiers.
Yeah, so what do we got?
So there, for every epsilon greater than 0, there exists.
So first,
there exists an x in the set.
Yeah.
For every epsilon. greater
Yeah,
than
there
0,
we go.
And then the set.
And then what does this become?
Not that.
yeah, let's just put it in there. That it's not contained completely inside the set. Oh, yeah, that's good. Just go simple and then work from it. So, for example, this set, closed interval, half open interval, A to B, that is not open because this point right here, this X, no matter what epsilon ball I pick around it, it's going to spill outside the set. So it's those edge points, those points that feel like boundary points. So I want to push this forward today. We're going to spend a little longer on this topology stuff than I was kind of thinking we might. What about so what were the results then? So the two results I asked you to prove. The first one was what? Cormac, what was that?
Prove that an arbitrary union of open set, blah blah blah, is open. Like a union of open sets is open.
A union, an arbitrary union, yes, of open sets is open. How did you proceed on that? I do want to collect whatever you did there, but it's just for light commentary and letting you fix it up easily. How did you start?
Let X be an element of the union of all the sets.
Cool, let's create the open sets though first. So how did you describe that?
The union, and then is that what you mean?
So first let's introduce the open sets,
Okay.
right? Because we haven't, how did you introduce those? It sounds like maybe you didn't.
I did not.
Okay, cool. Let's talk about how to introduce those. So and this is a notation style that you're probably not used to, but that's what I wanted to practice on. So this is an arbitrary, you're so used to things like this. K equals 1 to infinity, things like that. This allows for a countable collection, but this could be an uncountable collection. This could literally be for every real number, there is an open set associated with it. So this is the ultimate arbitrary collection. We don't know what size it is, doesn't matter, but it's got an index. We can grab any particular one out of it. So be a collection of open sets. Cool. And then you went to the union, it sounded like, Cormac. So let's talk about notationally. The union of these sets, union, and here I'm just gonna put alpha in A. I don't know what index set A is. Alpha is just an arbitrary index in there of O sub alpha. Okay. So now I think I'm caught up with you, Cormac. I just wanted to introduce, really lay out the definition clearly. What is each of these things? So now, how did you proceed from here?
Then X, let X be an element of the union.
I love it. So yeah, we're gonna take any X we want out of this collection. Love it. Okay. Then what?
Then X is included in some open set T.
Yeah, it's in one of these guys, right? If it's in the union, it's in one of these. So you're doing this exactly the right way. Then X is an element of O alpha prime. We'll just fix it for some alpha prime in the index set. We don't know what, but we know one. Cool, then what? That's great.
Then I argued that, so that set is an open set, so there exists a delta ball around X, which would be a sub-interval or subset of O prime, which is also a subset of the union. So then you chain the union or the subsets together.
That's beautiful. Yeah, very nicely done. So since this set, so it's in one of these sets. These sets are all open, so we'll just take one of the sets that it's in. Might be in multiple sets, we don't know, doesn't matter. But since this set is open, by the definition of openness, there exists some epsilon greater than 0, such that the ball of that radius around that point is completely contained in that one open set. And then I think I understood you right, Cormac, because this open set is then contained in the union, so is this ball. Was that your argument? Okay, cool. So by definition of a union, this ball epsilon is contained in O alpha prime, and that's contained in this arbitrary union. So this union is open. Took any arbitrary point, constructed an open interval around that point that's totally contained in there. Nice, good work. How does that feel? It's kind of straightforward, you just gotta be careful. What's that? That's an interesting look, my friend.
Makes sense. I don't know. I was just looking back through what I wrote.
Man, what were you thinking?
It's about the same. I think my wording is just confusing me.
It's all right. The word. If your wording's confusing you, we might want to work on your wording. Definitely, right? You want to be the one person it's not confusing to.
Yeah.
Do you want? So, what were you saying that you're feel like is a little weird? If you don't mind sharing.
I don't know. I think I kind of just got a little bit caught up trying to prove that if some element like X of a given set in like the overall collection, like just trying to prove that element is in like the collection if it's a part of like the set, and then I think I just introduced too many variables.
That could easily happen.
Yeah.
Is this proof making sense to you
Oh,
though?
totally.
Like just like, okay, cool. Keep it simple. Keep it simple. And then I'm pretty sure we had another one. In this one we had a finite collection. Is that right? Or what was the next problem I gave you?
The intersection of finite and many sets is open.
Thank you, Camilla. So now this next result is suppose that O, and here, since we have a finite collection, we're gonna index it with just K. That represents an integer or a whole value, and we're gonna let it run from 1 to n. I've got n sets is a collection, but it's finite of open sets. We need to show that the intersection of all these, so also practicing notation, is also open. How do I do this? How did you start, Camila, if I may ask?
My notation is all messed up based on that proof. Like
That's okay.
I did the same thing just with the completely like.
Cool, do you wanna, I wouldn't mind, I'd be curious, like, how you thought about it, so what were you
So
thinking?
this
We can
one,
use your
I was
notation.
like, I made a set O sub B be the intersection of the sets.
So you did this, so O sub B is the intersection of, and you basically just had
Yes.
a finite, no, okay, cool, so we'll do this. Okay.
And
Sure.
then I introduced an element X in the intersection.
Cool, so let's take X in, and I'm just gonna write this intersection again, cause, cool, I like that, that's what we need to do.
And then I named I said that the intersection O sub B, which I made, goes from the set O sub 1 to O sub n.
Mm-hmm.
And then since it's open, since the intersection is open, there exists a little o greater than the big O, where we can find a delta ball in the intersection.
So it almost sounds like you're assuming the intersection was open.
I think, yep.
Yeah, so we gotta pull back from that just a little bit. But we do know, so I like this. What does this mean? Let's just start, no openness. What does this literally mean right here, that that's in the intersection?
That there's like an element in one of the sets in the intersection, or it's not in the sets.
That it's in all of the sets. Yeah. So X is an element of O1, X is an element of O2, all the way, X is an element of O sub n. So it's in all those. Now each of those is open. So I can find a delta ball around X that's contained in here, one that's contained in here, all the way up. So since the O sub k's are open, for each k, there exists a delta ball around X. There exists, how about this, an epsilon sub k, such that the epsilon ball around X, the epsilon sub k ball, and this should be positive, is contained inside O sub k. Now let me stop. What am I saying here? What am I saying? Say it in a different words, in your words. Let's draw a picture. Let's do something a little chiller. So let's say I had 3 open sets. And these are just, let's say they just look like that. So there's O1, here's O2, and I'm just gonna write them kind of like this, and then here is O3. Imagine them all on that line there, but I just kind of wanted to put them here. So we're taking an X that's in the middle of all those. So there's our X. That's the X value. What can I do for each of these balls? Or these open sets? So this is open, this is open, this is open. What can I make for each one of these?
Different delta ball.
A different ball. So for each one of these, and that's what I'm saying here, there's a different epsilon for each one of these. So for example, for this X up here, this would be my ball that fits inside here. For down here, I could actually make it a little bit bigger. Down here, it looks like I could make it even a little bit bigger still. But that ball is contained inside that ball's contained inside that, and that ball's contained inside that. What can I do to create a ball that's inside all of them?
The minimum of
The minimum, I'm gonna take the minimum. Exactly, so what we're gonna do then is we're gonna let epsilon equal the minimum of the radii that we've already chosen out of the epsilon. Now these are all positive. Remember that the epsilons are positive that I've chosen. Why is it important to have a finite number here? Because remember, this result says a finite collection. This isn't true if there's an infinite collection. What if I had done this infinitely many times? What's the danger? If I have infinitely many balls and I've chosen epsilons.
just keep getting smaller, like there wouldn't necessarily be a minimum.
There might be an infimum, and that infimum might be 0. So what happens is if I allow for infinitely many balls to be chosen, their radius might shrink to 0, and then we don't have a ball at all. So the key thing here is that finitude ensures a non-zero minimum. So that's where the finiteness comes in. And then, once we've got that, let's do this. So then, ball of x sub epsilon is contained, since this is the smallest radius ball, this is contained in every single one of those O sub k's for k equals 1 to n. Therefore, it's in the intersection. Can you give me an example? And we did this last time, I'm just trying to think, I want you to think about it freshly on your own. Can you give me an example of an infinite collection of open sets, infinite collection of open sets whose intersection is not open? And it's good to be able to come up with these counterexamples. Christian, you look like you already have an example. What you got?
I was kind of thinking something along the lines of like, if you did sets kind of like decreasing on the interval 0 to 1, so like the first set would be 0 to 1, the next set would be like 0 to 1/2, next set would be 0 to 1/3, and then like keep going up, or keep going like that, where like
So
the upper bound has like the
that?
1 over it, exactly, yeah, and like you just go up through like the
okay,
natural
so let's see here. So we'll do something like that. That's what you're thinking.
Yeah.
What is that set?
Or
What's in there?
like in the intersection. or just
Yes, sir.
zero,
Yeah. What is
right?
this infinite intersection? What's left? What's inside there? What's a shorthand way to write what you expressed there?
0, right?
Is 0 in here? Because 0's not in any of the sets.
Oh, right, and that'd be the empty set. Okay.
It is the empty set. Let's make sure we see that. Is that open? That is open.
Could you then just change it and like say the set that contains 0 at the bottom?
We could, but then we wouldn't have
Oh,
open
that's fair.
sets.
Yeah, fair enough.
So I like, this is good. This was a good conversation. How could we tweak it? We could tweak it. Cease, you got anything here?
Change the 0 to -1/n.
Try that. And now it's got 0 in it. We're shrinking in on both sides. Yeah, perfect. And that's definitely a closed set. Does that make sense?
Yeah.
Or not an open set anyway. Anybody else come up with any other examples? We're on, okay. Let's talk about closed sets. Not necessarily the opposite of open sets, but kind of in a weird way. So let's talk about them here. So definition, a set F, and so that O we typically use for open, F is like the symbol for closed, or the letter, set letter we use often for closed. It probably is some German. Who knows German? I thought you knew German. No, you don't know German.
Count to 3.
Yeah, eins, zwei, drei. Yeah, I got you on that too. It's probably some German word for close. That's what I'm thinking. A set F is closed if, let's look at some things that are equivalent. F complement is open. What do I mean by complement? What does that mean?
All the elements that aren't in F.
Yeah, it's everything that's not in F. So this F complement is the real numbers minus F. So this is a cool way to tell if a set is open or closed. Or to tell if a set is closed. So let's just do a couple of quick examples here. What if I just have the singleton 0? So if F is equal to 0, what's F complement?
All the integers except for 0.
Or just all the real numbers except for 0, yeah? So it's just R minus 0. That's just this open interval and this open interval. Basically just skip over 0. And both those are open. They're like, we literally call them open. We've always called them open. But now you have a new sense of what that might mean. So both of these are open. And it's a finite union of open sets. It's open as well. Let's try another definition here. Or not a definition, but another way of looking at it. A set F is closed if F complement is open, but also if every sequence of points x sub n contained in F converges that converges. to some x means that x is also in F. So if we've got a bunch of points piling up, looking like they're headed toward a limit, that limit is also in the set. So let's do some examples here. Is this set closed or open or what? So I'm going to give you two sets here. The first one is going to be 1, 1/2, 1/3, 1/4 on down, and then the second set is going to be 1, 1/2, 2/3, 3/4, 4/5 on down. Take a minute. Are those sets closed?
I'm very conflicted.
Cool, that's great. Which one? First one or both?
Well, A,
Mm.
because if it converges to 0, but
Mhm.
0 is not in there,
Yeah.
doesn't that mean it's not closed?
Yeah.
So it's open.
It's not not
Oh,
open
because
either.
that
You
doesn't-
don't have to be one or the other.
Yeah, because it's not open. 'cause
Yes.
it's like a double.
That's right.
Okay.
Yeah.
So it's just neither.
Yep, it's. And we'll go through these in a minute, but just a quick sanity check. A is not open, not closed. Because you've got this sequence converging to 0, and 0 is not in there. Not closed. Because when we're converge to 0, and 0 is not an element of the set. Yeah, definitely. So what's your argument on that?
What looks like, everything after converges up to 1, and if 1's already contained in there.
Exactly. Yeah. How are you feeling on this one? Perfect. Nice. So, we're chatting to a few of you out there. This one is closed. So with this one, we see that sequence converging to 1, or it looks like it's converging to 1. Does that make sense? That this, Camille, is that cool with that? That this sequence here is converging to 1. And so if I toss 1 into the mix, I've sealed off that hole where things are piling up, or added the place where things are piling up. Closed because 1 is is an element of the set, and there's a sequence which basically looks like this, n minus 1 over n, and that converges to 1. So you've got a couple of other, are there any questions on either of these? We feel okay on those. Are either of these sets open? You're saying no, Cormac, why you say that? I agree.
I was gonna say you can't build a delta ball around one.
Exactly. These are very sparse. Open means there's thickness to your set at a minimum, right? It's a very special kind of thickness. But these are just collections of discrete points. There's a half, there's 1, and we're just all this stuff in between here. And we're missing one of those points. But around any one of these points, there's lots of space to spill out of the set. So neither of these, this is not open, not closed. This is closed, not open. And so for any set, we can have 4 states. We can have not open, open, closed, not closed. And all those things are completely independent. Let's actually do a few more examples and just think through this in terms of open, closed. So I'd like you to just take a minute. It says open, closed, neither, or both. The rationals. Take a minute on that. This set. Both those sets, the weird sets. Probably should get a little light up there. Sorry, I'm about to turn on the lights up there. Oh, man, terrible. Oh, I'm so sorry. That kind of sucks. I think we'll just leave them off. Yeah, that's no good. And the second one is something that we've brought up a few times. I just wanted to see. It's like one of those facts you're walking out of this class knowing, damn it. Whether you like it or not. Interesting. So, what's your argument there?
It just seems like you could build a delta ball around it.
They feel like there's a lot of them, right?
Mm-hmm.
Kind of thick. Okay. I do have a question for you. Do you remember density? Do you remember density of Q in R? How did that go?
Is that between any two rationals, there's infinite reals? Is it something like that?
Between any two reals, there's just always another rational. What? So, yeah. So for any A, B that are reals, A less than B, there exists a Q, and then we kind of did this other homework problem. There exists a Q and Q that's between them. remember we did a similar problem with the irrationals? Do we remember that? Kind of, that the irrationals are dense as well. So, same for the irrationals. So you give me two real numbers, A and B, no matter what they are, and inside between these two I can find some irrational. So if you're thinking, Cormac, okay, let's look at the cube. I'm gonna take some cube. I wanna find some ball inside here that's completely contained inside there. Why is that idea blown by the density of the irrationals?
The other numbers in there.
Because no matter what I make that radius, there's going to be irrationals inside here. So they're not open. They're weird. They're crazy. There's a lot of them, but they're broken apart. So this set here is not open, for sure. Is it closed? Why you say no?
So
I agree.
the complement would be the irrationals, right?
Yeah, so let's do it a couple ways. Complement would be the irrationals.
And you could use the same argument to say the irrationals.
Absolutely. Yeah, absolutely. Could someone give me a sequence argument? Could someone give me a sequence argument for to show that the rationals are not closed?
Oh,
What you think, Camille?
We use the same one that, like the one we were going through earlier, the 1/n sequence. Like if we take,
Let's see. So I want a sequence of rationals. So you're thinking in this sequence here. So those are all rationals, right?
and they would all converge to 0.
But that is a rational.
Right.
So can you give me a sequence that sequence of rationals that converges to an irrational? Do you remember how we were thinking about decimal expansions?
Yeah, that's what I'm trying to.
Yeah.
Remember the form, I guess.
So what's square root of 2? 1.4141, blah, 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 some crap like that. So if this is square root of 2, that's irrational. All I gotta do is just grab those decimal. Expand. Exactly. So I can just grab a decimal expansion bit by bit and get a sequence of rationals that converge to an irrational. So that's another way to see that that's not closed. Does that make sense? Okay, cool. What about this one? Is this open? What does this even look like? What the hell is in this set? What's the first thing in this set? What's the least thing in this set? Yeah, I think a 1. When n equals 1, we just got that guy. What's the next thing in this set?
1/4.
1 plus a fourth, so. Yep. So 5/4, and then that's the next thing in that set. Yeah, so I've got the partial sums. These are just partial sums of an infinite series. That infinite series was this one. That's the full series. What did that add to? Something, there was a 6 in there.
6 pi
Pi
over.
squared over 6.
This, yeah, we're getting it, yes, it's pi squared over 6, yeah. Yeah. Is that rational or irrational? That's irrational, right? We got pi squared, probably irrational because of pi. Is this number in that list? is pi squared over 6 in this list for any fixed n? Right, this is just a list of the partial sums. How does pi squared over 6 sit relative to this? Here's 1. Here's 1 plus a quarter. Shit, I don't know how to add 9 to that. Here's, and then it just, but I'm adding a little less, right? So here's the next one, and then I'm adding a 16th, and it's even smaller. So these things are kind of piling up, and there's a place here where they're going, the sum is headed as a limit, but we don't get there. So this is like a hole that's unfilled there, so pi squared over 6. So this set is not open. Excuse me, this set is not closed, because I have this sequence of points inside there that does not converge inside there. If I did this, if I unioned on pi squared over 6, now it's closed. It's like I filled the hole. Is it open? Why is it not open?
Can't make a delta ball.
Yeah, can't make a delta ball. About, here's 1 point right here. These isolated points, you can't make delta balls around them that are contained inside the set. So again, this is not closed, not open as well. All right, let's talk a little bit more, some properties here. Let's see if we can knock out, so we remember, we know this, that the arbitrary union of open sets is open, and that the finite intersection of open sets is open. So let's think about, what do we have for closed sets? How do closed sets and open sets relate? Very first characterization.
I was gonna say opposites, but
Yeah, that's the right feel. What's the fancy math word though? Not opposites, but
you're looking for like contradiction.
complements.
Complement.
That's what we're looking at. Okay, recall that the complement of a closed set is an open set. So let's take a look here and say that I have an arbitrary intersection of open sets, of closed sets. So I've got this collection F sub alpha. Alpha is in some index set, I don't know what it is, there could be uncountably many of these, so I've got this, and I want to take a look at the intersection and think about that. How could I turn this into a problem about open sets?
Complement.
Take the complement. How do I take the complement of an intersection? What is the law that we're thinking of here, or maybe not thinking of? I think you all kind of are thinking of it. If I have A intersect B, and I do the complement of that, what is that equal to?
Is it A complement union B complement?
That's it. What do you call that law? Exactly. Nice.
That what it's called.
De Morgan's. So this is De Morgan's law. Very important law, comes up a lot of different places. We've got this one as well. Vaguely familiar. Those are super helpful things here. So now, this complement here of the intersection is equal to the union of the complements. So now I've got the union of open sets. It's an arbitrary open set sub alpha. What do I know about arbitrary unions of open sets? They're what? They're open. So here, look, we've got an arbitrary union of open sets. This is open. Because of the basic property, because let's see, what do we call that? The union property of open sets. So check it out, this complement is open. So what does that say about this? Therefore, this complement, or the original set, if the complement of this is open, what can I say about this? It's closed because its complement was open. So check this out. For closed sets, arbitrary intersections are closed. Let's actually summarize that really quickly here. So arbitrary intersections of closed sets are closed. So it doesn't matter how many you have. As long as you're intersecting and they're closed, you get another closed set, no worries. But only finite unions of open sets, of closed sets, are closed. This is the companion to this one about intersections and open sets. Over here, it's unions and closed sets. You can only have finitely many. Can you give me an example of a collection of closed sets whose union is not closed? So I want a bunch of intervals of some kind. They're growing, maybe, or shrinking. Can you give me a collection of an infinite number of closed intervals whose union is open? So take a minute and think about this. My hint would be have them kind of expanding. what you got there? Yeah. So you're saying these guys here? Did I write that right?
Mm-hmm.
Okay, so let's see, what would our intersection be? So let's see, so F1 is this guy, F2 is this guy. What were you thinking the intersection was? Definitely we got a 1 in there, right?
0
So it seems like 0. Is 0 included?
and no. Or
So we're coming in on this side here, right? We're kind of moving in there. I think 0 is gonna be in every single one of these. Just because that left edge is negative. So for example, what I mean is, that's true, right? That 0 is always in there. So since 0 is in all of them, I think that this intersection here is actually the closed interval 0 to 1. I think 0's in there, but it's close, But I think we need to expand as opposed to contract. So, Corbett.
Well, are we doing union?
Oh, we are doing union. Yes, thank you. Yeah, so we were doing union. So on these, if we were doing the union of all these, I think it would actually just be this first guy. Cause it's the biggest one, and if we're taking unions of all of them, it would just be the one that contains them all. But I think, see, so we could, if we just made that a positive like that, now I think we've got a good troublesome one. So if I take the union, n equals 1 to infinity of these guys, and maybe we should start at 2 so we don't have that weird, strange not defined interval. So let's see here, so we're gonna have 1/2 1, and then 1/3 1, and so this left end is gradually moving this way when I've got 1 over n1. I don't think 0's in there. So 0's definitely not in any of those elements, any of those basic sets. But I can get as close to 0 as I want, so I think that this thing here would look like that. Does that make sense? And should I talk about how I would prove that? I'm happy to do that. Let's actually think about why this is the case. So this set here, let's get back. Here's my claim, is that this is 0 to 1, not including 0. And the way you think of this is you've got these intervals, here's 0, here's 1. They're swelling and they're getting closer and closer to the 0, but they never get there completely. But they're definitely pushing as close as you can to that. So if I took a number over here, so if I took some x in here, then that x would be less than 1 over k for some k. Do you remember the Archimedean principle? Just vaguely, if I tell you I've got some number that's really tiny, x, I can find some number, I could find some k so that 1 over k is to the left of that. How about that? So I can find some k large enough that it lives to the left side of x, so I can have 1 over k is less than x for some k. Find some 1 over a billion, 1 over a trillion, blah, blah, blah. So this would mean that x was an element of this interval. And here's that interval right here. It goes all the way up to 1. That's the interval that starts at 1 over k. And from that point out, x is in the union of all of them. Therefore, x is in the union of all these things. Because because I found one of them that it's in. Yeah. You guys doing okay? Is everybody okay? Feeling like the energy, I just feel like it feels quiet, low energy in here today. I'm not blaming you. I almost feel like I'm feeling like quiet. I'm not putting you to sleep, am I? Are you sure, Camille? Okay, cool,
It's
cool.
not you.
Okay, yeah.
It's not you.
It's all of us. It's just all of us. Cool. All right. Let's push forward a bit. One more definition here. Probably one of the most important set types in all of real analysis. And a word you probably haven't had a lot of experience with. You might have never even seen it before today. But we say a set K is compact. Now this is gonna, some weird stuff's about to happen, and this is kind of awesome. It's gonna make our brains grow in incredible ways. Is compact, and this is of course a real subset. If K is closed and bounded. And that's just one definition. That's the simple definition. We're going to get into some more interesting ones very quickly. But set K is compact as long as it's a subset of the real line, if K is closed and bounded. So think about what closed means, right? Any sort of limit that exists inside the set, its limit point is also in the set. So let's put some things here. Contains all limit points of sequences in the set. And bounded, what is bound? What's a good definition of bounded? What's a good definition of bounded? What's a professional grade? Now I'm making it harder. What's a professional grade definition of bounded?
Just the set has a supremum and femum.
That's true. Yeah, okay, I'll buy that. Or just even more simply, bounded. Bounded means, let's see here, K bounded means there exists some M such that everything inside there is bounded by that M. We don't have to get, we don't have to get super fancy, right? In other words, this set is bounded if it doesn't fly off to infinity, right? I can put it in some little window. It's no more than M units away on either side. So, this is pretty intuitive. Is this set compact? Compact. Why not?
It's open.
Because it's open. Nope. It's open. Is this set compact? Is that set closed, by the way? We know this one's not closed because it just doesn't look closed. And it's missing the 0 and the 1. right? If it had the 0 and the 1, is this closed? What's its complement? That's its complement. Is that open? Sure feels open. So this must be closed, even though it's big. So this is closed. What's the problem that's keeping it from being compact?
It's not bounded.
It's not bounded. Exactly. So this one up here was open, but it was bounded, but we needed both of them to be compact. Is this set compact?
No,
Yeah, why not?
that one's also unbounded.
Is it closed? Why do you say that, Cormac? I agree.
Its complement is open.
Its complement is open. Its complement is just all these open intervals between the integers, right? Just a union of open intervals, the complement. So Z complement is a bunch of open intervals. That's clearly open. So this is closed, but it's not bounded. So it's not compact. What about this one? All the rationals in 0 to 1. Think that's compact? Is it bounded?
Yeah.
That one's easy, right? We got bounded. Is it closed?
No.
Why not?
Because we were talking about earlier where irrationals are more dense than the rationals, and so for any, like you could choose like a delta ball that wouldn't be in there.
Yeah.
Because like it would have like the irrational as like its delta.
Yes, this is, there's a lot of truth in the words you're saying there.
I feel like I'm mixing something.
It's there, I agree, I think that's true too. But if I take some rational inside there and try to find any ball around it, so plus epsilon, minus epsilon, so that's q minus q plus, there is some irrational inside there, no matter how I do it. So there's, oh, this is what you were trying to get at, I think. That, so this is not closed. Because there are sequences of points in there that converge to things that aren't in that set. So for example, there exists a sequence converging, a sequence of rationals converging to square root of 2 over 2. Which is like 0.707-ish. That's an irrational number, just do the decimal expansions. 0.7, 0.70, 0.707, blah, blah, blah. So this is an important point, right? I've been making this point a lot about these rationals having limits that are irrational. That's one of your key places to go to find things that mess up things. Before we end today, I want to talk about one of the more interesting ways to think about compact sets. So this is quite strange, but we need a definition. Given a set S that is a collection of real numbers, an open cover of S is a collection of open sets, and here we'll just say O sub alpha, alpha is in some index set, I don't know how big it is, could be countable, could be uncountable, could be finite, doesn't matter, is a collection of open sets whose union covers S, whose union contains S, i.e. S is a subset of the union of all those sets. Stop for a second. here. If S is the set 0 to 1. And I let for each x in that set, let ball of radius 1 around x be an open set containing x, and we don't have to let it, it just is, then the collection of all unit balls, so that 1 there is just radius 1 for x in the set S, is an open cover. Let's do a weirder one. So let's let Q. If we put a ball of radius 1/2 on each rational, we have an open cover of the rationals. It's basically just making sure you just got a bunch of open sets and you lay them down on top of your set and it completely covers of it. Let's look at a less insane example. Simpler example. Let's say my set is again closed interval 0 to 1, and I'm just going to pick 3 sets. O1 is -1/2 to 1/4. O2 is I want to make sure it overlaps with that 1/4, so we'll say 1/8 to 3/4. And then O3 is 1/2 to 5/4. This is an open cover of S. So this is an open cover of S. And to see that, you just kind of got to draw it out. So here's S, 0 to 1. My first set goes from -1/2 to 1/4. So let's see, there's 1/2, there's 1/4. So this first set kind of runs like this. This is O1. O2 runs a little bit left of that to 3/4. So there's O2, and then O3 runs from 1/2 all the way out to 5/4. But notice that the union of all 3 of these covers S. So union of, well, we'll just put it here, O1 union O2 union O3 covers S. That's an open cover. This is an infinite open cover, because there's infinitely many things. This is an infinite open cover. This is a finite open cover, because there's only finitely many sets used to cover it. It's a very, very weird idea. Where could we be going with this? And where we're going is a place we'll pick up a little more on Wednesday. Set K is compact, and this is the definition of compact that applies everywhere. You would, in a lot of books, you would just get this right up front. Is compact if and only if every open cover of K allows for a finite subcover. Okay. So this is a really weird thing. I just want you to just think of it for a second. Think about it. I'm going to try to write it up here in different words. I.e., no matter how we cover K with open sets, we can always grab a finite subcollection of those sets that covers K. Maybe one of the weirdest things you probably have ever seen in math. Like, it's still weird to me. It's a very strange characterization, but we're gonna play with this. We're gonna play with this. So that's another way to think about being a compact set. So what were the things we knew about compact sets? They were closed and bounded. So this is equivalent to K is closed and bounded. So let's see how we can actually break this open cover thing. Let's look at some sets that aren't compact and see how we can cover them in a way that doesn't allow for a finite subcover. So example, 0 to 1 is not compact. Why is it not compact? Let you get caught up there. Why is 0 to 1 not compact?
Unbounded.
It's open. Definitely bounded, right? But yes, so it is open because it is open. So we know it's not compact. That was our definition. Let O sub n equal 1 over n. And this is kind of going back to something you were talking about. We were talking about just a little bit ago, Cecil. Let's let O sub n be these sets. For n equals 2, 3, on up. What do these sets look like? Here's 0, here's 1. They basically have this left endpoint that starts there and goes to there. And that left endpoint's moving this way as n gets bigger. So the union of all of these, and we're starting at 2, is actually completely equal to that interval. So let me stop and write that. Does that make sense to you? Do you believe that? Because you tell me any element out of here, any element out of there, certainly is, everything in any one of these O sub n's is certainly in here. And over here, all I have to do is you tell me you picked like, oh, I picked x as like one really tiny number, it's 1 over a Google. Well, all I have to do is pick this n big enough and your number you picked was in there. I can slide this n further past any number you can give me. So this is the case, but there is no finite subcollection of these that covers that. There's no way I can take a finite number. I need the infinite number of these because they have to creep towards 0. But no finite subcollection O sub n1 through O sub nk can cover this interval. Why is that? Why is that? Why does no finite subcover work here? And then we'll call it for the day. O sub n1 looks like this. O sub n2 looks like this. What's the furthest left these things will reach? And then we go all the way out to O sub n sub k is 1 over n sub k comma 1. What's the furthest left?
Over n sub k.
What, depending on which one of these is the smallest left
Yeah.
end, right? So at some point though, whichever, if you take the max of the n1 through the nk, then 1 over n, let's call that m, then 1 over m, the max of those is as far left as those things can reach. So there's always going to be this gap here that is uncovered. So this set is not compact because there is some open cover that does not allow for a finite subcover. Compact means no matter how I cover it with open sets, I can always find a finite subcover here. So because there exists some open cover with no finite subcover, see, I just have to come up with one. The set is not compact. And I think on Wednesday we'll kind of get into the proof of why that's the case. So no homework, does that sound okay? Do you have something, you got something you wrote up for me today? I'll take a look at those. Thank you, oh, okay, all good, thank you. Many thanks.
Also,
Yes,
this
thank you.
is just a little correct on
Okay, that's great, thank you. Well, put them where,
that.
you put where? Thank you, awesome, thank you. Is this from CC?
Yes.
Thank you. I gotta go pee pretty bad. I'll catch y'all on the flip side. Oh shit, that's all in here. Great.